the photoelectric effect and the particle nature of light. Before we can study the photoelectric effect, we need to look at the electromagnetic spectrum. There's some facts that you really need to know very well. The electromagnetic spectrum is made up of 7 parts, from gamma rays right down to radio waves. So the highest frequency electromagnetic waves are the gamma rays. They go from gamma rays to X-rays, then ultraviolet, then a small section is our visible light, infrared, microwaves and radio waves. Radio waves have the longest wavelength, gamma waves have the shortest wavelength. The shorter the wavelength, the higher the frequency, the longer the wavelength, the lower the frequency. All of these waves are transverse waves. They all travel at 3 × 10⁸ meters per second. This value is given to you on your data sheet. They can all travel through a vacuum. They don't need any mechanical particles to move. And they all obey the wave equation, where we can say V for speed is frequency times wavelength. But when we speak about electromagnetic waves, we can use a C in the place of the V, where C is 3 × 10⁸ meters per second, as mentioned over there. Electromagnetic waves carry energy in packages, and we call these packages photons. Think of photo, which has to do with light. The energy of the photons is dependent on the frequency of the electromagnetic waves. And as you can remember from the previous sketch that we had, gamma rays had the highest frequency, so the photons would have the highest energy. It's all according to this equation. This is the energy of your photons of your electromagnetic waves. So the higher the frequency, the higher the energy. H is Planck's constant, 6.63 × 10⁻34 joules times second. Please remember it's not joules per second. Or you can give the equation as Planck's constant times the speed of electromagnetic waves divided by the wavelength, because frequency is equal to speed divided by wavelength. The higher the frequency of the photons, the greater the energy of the photons. The more the photons will behave like particles if they have high frequency. So obviously then gamma rays, which have the highest frequency of all electromagnetic waves, will have the highest energy, and they will behave the most like particles. If we take this equation and we make our constant a 1, the equal sign becomes a proportionality. So energy of your photons is directly proportional to the frequency of the photons. They can ask you to draw the graph for this. It is normally not in your textbooks, or it will be one of the options for a multiple choice question. So frequency of your photons determines the energy of the photons. It's a direct proportionality, therefore it is a straight line graph through the origin. So I've used X-rays as an example. They're the second highest section of on our range of electromagnetic waves. After gamma rays, X-rays with a very high frequency have more particle nature than wave nature because they have high energy. The higher the energy of the photons, the more they behave like particles. We are now going to look at the relationship between the energy of the photons and the wavelength of the electromagnetic waves. If you remember again, gamma rays were on the left-hand side of the sketch, so they have the shortest wavelength. The shorter the wavelength, the greater the energy of the photons. It comes from this equation. H is Planck's constant, C is the speed of all electromagnetic waves. These two values are constants. Make them a 1 and your equal sign becomes a proportionality. So energy of your photons is inversely proportional to the wavelength. Do not say indirectly, use the word inversely. If we plot a graph of the energy versus the wavelength, we'll have an inverse proportionality graph. But if we plot the graph of energy of the photons versus 1 over wavelength, that is a direct proportionality, so that will give us a straight line graph. To get back to the particle nature and the wave nature of the spectrum, the lower the frequency of the photons, the lower the energy of the photons, they will behave more like waves. So for example, microwaves, which are second from the right-hand side on the sketch that we have, they are the second shortest of all our electromagnetic waves. They have low frequency, therefore long wavelength. They will have more wave nature than particle nature. The invisible light, it falls in the middle of the electromagnetic spectrum. It therefore has dual nature. It has wave nature and particle nature. You might hear someone talk about the dual nature of light. That is because light, visible light, has wave nature and particle nature. One more graph that I would like to look at is the graph of frequency versus wavelength. Remember from our wave equation, the speed of electromagnetic waves is equal to the product of the frequency and the wavelength of the waves. The higher the frequency, the lower the wavelength, or the lower the frequency, the longer the wavelength, because these two values always have to multiply to give you the same constant, 3 times 10 to the 8 meters per second. So frequency is therefore inversely proportional to wavelength, and our graph would give the inverse proportionality. If they ask you to draw a graph of frequency versus 1 over wavelength, it would be a straight line graph through the origin. The higher the frequency, the shorter the wavelength, because frequency and wavelength are inverse proportionalities. In grade 11, you did 2 chapters on wave nature. You did a chapter on the refraction of light using Snell's law, and you also did a chapter on 2D and 3D waves, which involved diffraction and interference. So diffraction, interference, and refraction are all proof of wave nature. Proof of particle nature is the photoelectric effect, and that is what we are doing in grade 12. So you must know the definition of the photoelectric effect. It is the process whereby electrons are ejected from a metal surface when light of suitable frequency is incident on that surface. In order to eject electrons from a metal, the frequency of the incident light must be greater than the threshold frequency of the metal. Each metal has its own particular threshold frequency. So if your frequency of your incident light from the electromagnetic spectrum is greater than the threshold frequency of the metal, electrons will be emitted or ejected from that piece of metal. Another word for threshold frequency is called the cut-off frequency. The definition of threshold frequency or cut-off frequency, it is the minimum frequency of light needed to emit electrons from a certain metal surface. The symbol that we use is a small letter F with a subscript 0. Please make your subscripts look like subscripts. A lot of you are being penalized in your tests and exams because your subscripts are written too high or too big. The definition for the work function, which is a capital W for work with a subscript 0, work function is the minimum energy that an electron in the metal needs to be emitted from the metal surface. So to calculate work function, it is Planck's constant times the threshold frequency for that particular metal. Threshold frequency and work function are set, or they are fixed for each particular metal. That does not change. If the energy of the photons is greater than the work function of the metal, electrons will be emitted with a certain kinetic energy, Ek. The following equations are all extremely important, but they are given to you on your data sheets. This is the energy of the photon that is incident on the metal. So there's your electromagnetic photon incident on the metal. This rectangular thing here is our metal, and these are our electrons inside the metal. The work function, W0, is the amount of energy needed to get the electron from within the metal to the surface, and then if there's any energy remaining, that will be the kinetic energy with which the electron moves away from our metal surface. E is calculated by Planck's constant times the frequency of your incident light. There it is. W0 is your work function, which is calculated by Planck's constant times the threshold frequency of the metal. And Ek is the normal equation for calculating kinetic energy, half mv squared. The mass of an electron is given to you on your data sheet. Please remember that. You might get a question in the exam and they don't give you the mass of an electron. You do actually have it. It's on the data sheet. A quick look at the sketch again. This is the photon of light from your electromagnetic spectrum falling in on your metal. E is equal to HF in red. There we go. The work function in green is the energy needed to get the electron to the surface, and then the energy in blue is the kinetic energy of the electron as it moves away from the metal surface. If your energy of your photon is equal to the work function, your electron will just be able to go to the surface. It will have no extra kinetic energy to move away from the surface of the metal. The electrons that are removed from a metal under the influence of photons are called photoelectrons. They are normal electrons, but they're called photoelectrons. We are now going to study the kinetic energy versus frequency graph for the emitted electrons. For now, just ignore the graph and look on the right-hand side. If we consider the general equation for a straight line graph, you know it is y equals mx plus c, or f of x equals mx plus c. This is your vertical axis, so in this case it's kinetic energy. M is your gradient, x is your horizontal axis, in this case it is the frequency of the incident light, and c is your y-intercept. We are going to arrange our equation, which was E equals W0 plus EK, but in the place of E, I'm putting in HF, and we are going to manipulate this equation to fit the axes of the graph. So I want EK to be on the left-hand side where the Y is, because it's my vertical axis, and I want frequency to be in the place where X is, because that is my horizontal axis. So the equation becomes this: EK equals HF minus the work function. So I made EK the subject of the equation. If you minus work function on both sides, it becomes HF minus work function. So that is what our equation looks like now. It is the same form as the general equation for a straight line graph. Y equals mx plus c. Y is our EK, our vertical axis. H is m, which is the gradient. So you can see the gradient of this graph is Planck's constant. The slope represents h, Planck's constant. X, in this case, is our frequency, and c is our work function. So the y-intercept of this graph is the work function. You can see this is an energy and work are in joules. This is our energy axis, and that is our frequency axis. The x-intercept, or the frequency intercept, is the threshold frequency of our particular metal. And once again, the slope is the gradient is Planck's constant. So this is the graph for EK equals HF minus work function. There the equation is. W0, work function of the metal, is the intercept of the vertical axis, and the gradient represents Planck's constant. All of these graphs will have the same gradient, irrespective of which metal we use and irrespective of which section we use from the electromagnetic spectrum. As you can see from this graph, any frequency lower than the threshold frequency will not give the electron any kinetic energy to leave the metal. The frequency that is equal to the threshold frequency will not give the electron any kinetic energy, but it will just get the electron to the surface of the metal. If I choose a frequency slightly higher than the threshold frequency, say for example a frequency over here, you would take that frequency, draw your dotted line up to your graph, draw it across, and then you could read off what the kinetic energy of that electron would be as it leaves the metal. The higher the frequency of the incident light, as long as it's above the threshold frequency, higher frequency will give your electron a higher kinetic energy as it leaves the metal. In this sketch, we have a few graphs for different types of metals, the same as the previous graph. On the vertical axis, we have the maximum kinetic energy of the electron, which is leaving the metal. On the horizontal axis, we have the frequency of the incident light. The threshold frequency is given for each particular metal. As you can see, each particular metal has its own threshold frequency. So we'll look at potassium first. There's the threshold frequency. Potassium has the lowest threshold frequency. There's its work function. For sodium, the work function will be lower down. It will be where it intercepts with the vertical axis, and its threshold frequency is higher. It has greater work function and greater threshold frequency. If we go up to platinum, of all these metals, platinum has the highest threshold frequency, so it needs the most energy to get an electron to the surface. I want you also to notice that all of these graphs have the same slope. They have the same gradient, because the gradient represents Planck's constant. It will never change. You will always have the same gradient. You have the value for Planck's constant, 6.63 times 10 to the negative 34 joules times second. So if you were ever asked to calculate anything from a graph like this and you have certain values that you can read off, remember you have the gradient of the graph. The question above the graph is, which metal requires the greatest or minimum energy to begin to eject electrons? Which metal requires the least energy to eject electrons? Potassium requires the least energy. It's got the lowest threshold frequency and the lowest work function. Potassium requires the most energy to release electrons because it has the highest threshold frequency and it would have the highest work function. The next question, what does this mean with respect to how tightly electrons are bound to an atom? In which one would you say are the electrons the most tightly bound? In which one would require more energy to remove electrons from the atom? Platinum would require the most energy from a photon to remove electrons from the surface of the metal, because platinum has the highest threshold frequency, and if we had to extrapolate this graph back down to the vertical axis, it would also have the greatest work function. So in platinum, the electrons would be more tightly bound to the atom than in potassium. Potassium has the lowest threshold frequency, it will have the lowest work function, therefore it would lose electrons the easiest. Of all of these metals, platinum would require the most energy to have electrons removed. You may get a question involving an electroscope. An electroscope is just an apparatus that, when it is positive or negatively charged, the gold leaf will move away from the other piece of metal because they have the same charge, so repulsion takes place. In the first example, your electroscope can be positive or negatively charged, but so that when red laser light is shone on it, you know that red light has got a low frequency, therefore low energy of the photons. So whether this electroscope is positively or negatively charged, it won't have any effect. So there's no effect on the electroscope. Our next electroscope is positively charged. That means that electrons have been removed. So the positive gold leaf is repelled by the other plate, which is normally zinc or platinum. So the gold leaf is repelled by the other metal. If ultraviolet light is shone on the positively charged electroscope, nothing happens because ultraviolet light has a very high frequency, therefore high energy of the photons. So it can remove electrons, which would just make the electroscope more positively charged. So in this case, nothing happens. There's also no effect because your electroscope is positively charged. It has too few electrons, so there's very little chance that your ultraviolet light will remove more electrons. In the third example, our electroscope is negatively charged. So something was done to give it a negative charge. So while it's negatively charged, it would look like this. The gold leaf would also be repelled by the other metal because they both would be negatively charged. But when the ultraviolet light with high frequency, therefore high energy, is shone onto the plate, electrons will be ejected or emitted from the electroscope. So the plate will lose those extra electrons and the gold leaf will go down. The difference between these two is ultraviolet light shining on a positively charged electroscope. It has already lost electrons, so it won't want to lose more, so no change takes place there. In this one, the electroscope is negatively charged, so when the high frequency ultraviolet light, high energy photons shine onto the metal, electrons will be removed, so it will lose its negative charge, and the plate, the gold leaf, will go down to the other metal plate. In this sketch, we will be looking at the photocell, which works under the influence of incident light. Photons fall onto the cathode, electrons are emitted, and they move towards the anode and flow through the external circuit. An ammeter or micro or milliammeter is used to measure the current strength. The cathode is connected to the negative terminal of the cells, and the anode is connected to the positive terminal of the cells. So your intensity of your light determines the current strength. But just remember that the frequency of your incident light must be greater than the threshold frequency for electrons to be emitted. An increase in the frequency of the incident light will increase the kinetic energy of the emitted electrons. If we change this equation to what it is on the right hand side, all I have done is replaced E with HF. The greater the frequency of your incident light, this is constant for the metal, the greater the kinetic energy of the electrons moving away from the metal. But if we change the intensity of the incident light, in other words, a brighter light, if you increase the intensity of the incident light, that means you have increased the number of photons falling in on the metal. This will increase the number of electrons emitted from the metal, and that will lead to an increase in the current strength measured by the ammeter in the photocell. So do not confuse these two, an increase in frequency with an increase in intensity of the